us. While the electronics story continues to unfold in amazing ways, the story is beginning all over again with a materials revolution in medicine. It's not a new idea. Remember this?
Phase 1 calls for miniaturizing a submarine and injecting it into the carotid artery. Stand by.
Fantastic Voyage. It was the sci-fi smash of 1966.
Phase 1. Phase 1.
Scientists shrink a team of doctors and send them into a sick man's body on a mission to cure him.
All stations, stand by. Tracking post. Inject.
Today, as our devices get smaller and smaller, Fantastic Voyage is beginning to look like prophecy. The kind of thing that can change lives.
Hi, Courtney.
Hi, Dr. Mishkin. How are you?
Good, yourself?
I'm good, thank you.
Today, Courtney will be taking a pill. But it's not just any pill. It's a miniaturized camera.
This capsule is a miniaturized camera. Every time it blinks, it's actually taking a picture.
Oh.
It's acquiring images at a rate of 2 frames per second.
Okay.
And what I'm going to get you to do is actually to swallow the capsule.
Okay.
And as the capsule goes through the GI tract, it's going to be taking pictures of what's going on inside.
Wow.
It's called the pill cam, and it travels through the body just like a piece of food, taking 55,000 pictures over the course of 8 hours.
Why don't we actually put it inside your hand?
Pictures that can provide a diagnosis that once would have required surgery.
Right, so as you move it around, we can actually see the folds of your hands with excellent magnification. So once we actually go ahead and ingest the capsule, it's going to give us that same magnification of what's going on inside.
Wow. That's really cool.
It actually has a wireless transmitter that's going to transmit the images to the data recorder that you're wearing over the course of the day. And I'm going to download the images and be able to look at them and analyze exactly what's going on.
The pill cam is made of an inert plastic that doesn't create a toxic response in the body. Inside is a mini catalog of the electronics industry. A tiny video camera and flash, a radio transmitter, a battery, and of course, a computer chip to drive it all. 25 years ago, all of those components would have taken up a cubic yard of space. Today, it all fits inside a 1-inch capsule that weighs only a fraction of an ounce.
So let's go ahead and ingest it. Okay.
Hey.
Ready? Into your mouth. Give me a glass of water. So now I see your teeth. And go ahead. Down the hatch. Okay, great. So that's it. That's the hardest part.
Okay.
Just remember, over the next 2 hours, do not drink anything. So
Okay.
2 hours
As the pill cam moves through Courtney's digestive tract, it records what it sees, eventually giving Dr. Mishkin a front row seat as he looks for abnormalities.
Right now, we're looking at the small intestine. It's able to see 360 degrees, such that it's like looking down a gun barrel. The capsule is great at acquiring images, but I'm hoping that as the next generations of this capsule develop, that it's not only going to be able to take pictures, but that we'll be able to potentially biopsy, sample the tissue in that area, or even deliver a treatment, such as placing a clip on a bleeding site, or even deliver medications.
The pill cam is the pocket watch of today, a super miniaturized machine that liberates the patient. It took centuries to make the leap from mechanical watches to computers. But in the world of microscopic medicine, the story of smaller is unfolding on a vastly accelerated time frame. In fact, scientists are on the verge of realizing a 21st century version of the Fantastic Voyage story. They're developing microscopically small robots that travel into the body's deepest reaches to diagnose, treat, and even destroy deadly illnesses. This is your lab?
This is my lab.
This is where you build your robots?
This is where we build the robot. Yeah.
This is Brad Nelson. He's created a robot that could help cure blindness. It's incredibly lifelike.
Yeah, that's a mannequin.
Oh, sorry.
These are the ones we built.
What? That's a robot?
That's a robot.
Looks like a splinter.
Well, this is a micro robot. We use them to help perform surgeries on the eye or inside of the eye.
The device is only 1/100 of an inch wide, small enough to fit into the needle of a syringe, like the tiny sub in Fantastic Voyage. But the similarity ends there. This unmanned device is designed to treat a type of blindness caused by blocked blood vessels in the retina, the tissue where images are formed. robot delivers an extremely small dose of medicine to restore blood flow and vision. That makes me think the thing has batteries and little propellers and some kind of knowledge to know where to go in the eye. I have a hard time believing that.
That's right. So the way we energize this is we use externally generated electromagnetic fields. So basically, it's a magnet.
To make the device small enough, Brad had to abandon the idea that robots have to be mechanical.
Copper-colored thing here.
Instead, he focused on finding a material that would let him eliminate bulky moving parts. He chose two elements, samarium and cobalt. Combined, they form a material highly sensitive to magnetic fields, which means that Brad can direct the movement of the robot without touching it. Once again, a material replaces a machine, and the device gets smaller.
So then, besides just the robot, what we also have is this system here of electromagnets. And so what each of these copper coils do is they generate magnetic fields.
Oh, man. Yeah, I got a bunch of them every
And
direction.
so we have 8 of these here. That's why we call this the Octomag.
Octomag?
That's right.
The Octomag. By adjusting the strength of these 8 electromagnets, the surgeon can move the micro-robot any direction along the X, Y, or Z axis, pushing or pulling it through the eye. But landing it on the tiny section of retina that's used for seeing in sharp detail takes lots of practice. And you've been practicing with dummy eyeballs so far?
We use that, but we also use animal eyes as well. We get pig's eyes from our local butcher. So
You buy eyeballs from the butcher, from cadavers, or?
that's right. Christos, one of my PhD students here, Christos goes in the morning, early in the morning, to the butcher and asks for eyeballs.
Christos, how are you?
Fine,
Oh, hi. These are the pig eyes.
exactly. 20 pig eyes, fresh from the butcher, ready to be prepared for experiments.
He must be a big hit around Halloween. What about this guy? What's this all about?
We call him Mr. Pig Eye Guy.
Mr. Pig Eye Guy?
Well, you have to give them a name. And then we put the eyes at this hole here.
Once the eyeball is secured inside the socket, we insert a light probe.
So that's the light there.
Oh, I can actually see the light in there. Very cool. This tiny LED lets us see what we're doing when we drive the robot. So this is the robot right here? Mm-hmm. Okay, and this isn't fake. We're really seeing this live from the microscope right now, right?
Yes.
All right.
Now, you can move this guy around.
Okay, sure enough. I push right, he goes right. Left, he goes left. Let's see, I want to go down over here.
And then you can pull up. And
Oh,
you
it's
can
getting
see.
bigger. Yeah.
Exactly. This means that it's moving higher away from the retina. And
Closer to the surface of the... Oh, man, I think I just banged the top of the
exactly. So
cornea or whatever.
that's the very top. And this is where the liquid ends. So you
Okay.
see this effect.
Now let me push
When
down.
you push down, it starts slowly going into the retina.
Wow, that's really cool.
So now you've reached the bottom. You're touching the retina.
Yeah, it's quite responsive. You can go right up here. Eventually, Brad hopes that there will be a commercial version of his device installed in doctors' offices. The magnets will be arranged in a housing that surrounds the patient's head, while the doctor peers through a microscope to guide the drug-filled robot. Brad's initial success combining materials and magnetic fields to make tiny devices has encouraged him to be even more ambitious. His goal is to build a robot that can swim through blood vessels. But along the way, he's discovered that the smaller you go, the stranger the world becomes. Oh dear, looks like the grad students have left their things out again. And the harder it is to get around.
So what we've seen so far, the micro robots for the eye, we're interested in going even smaller and trying to make smaller robots. So I set up an experiment here to kind of show you what some of the problems are when we try to make small things swim and why it's so much different than how big things like fish or toys like this swim in water.
Okay.
So what we've got here are 2 tanks. One is just regular water out of the tap.
Yep.
But this other one's glycerin. It's much thicker, kind of like oil or corn syrup, something thick like that.
Okay.
So let's look at how something like this toy goldfish is going to swim in water.
Wind her up.
Wind her up and
All
let her
right.
go. Yep.
Okay, the tail goes back and forth.
Just the way you'd expect.
Yep, say that swimming is fairly effective.
Okay, he's got a twin over there. Let's see how he does in glycerin.
All right, and this one's going to go in the goop. And he wags his tail, and he doesn't move at all.
This helps us illustrate how water feels when you get small. So if you took yourself and you made yourself about 10,000 times smaller and you jumped in this pool of water, you would actually feel more like you were swimming in glycerin here, or goopy stuff like honey or something thick like that.
A swimmer the size of a bacterium would never be able to get around using flippers or the breaststroke, because at that size, the friction from the water molecules becomes a major drag. For a long time, scientists couldn't figure out how bacteria were able to swim, but eventually they discovered the secret. The tail, or flagellum, seems to move back and forth, but viewed from another angle, it's clear that it moves in a totally different way.
Corkscrew tail.
A corkscrew tail.
Brad and his team have developed corkscrew robots that mimic bacteria.
Bacteria like E. coli and Salmonella have developed these flagella that twist.
This part is the flagella?
This flagella twists through the liquid, just like a corkscrew going into a bottle of wine. So instead of propelling itself or using its inertia, it's actually kind of cutting through the fluid.
It's almost pulling itself instead of pushing
It's pulling itself in a sense, like a screw going into wood or something like that. It's a completely different material interaction.
Very cool.
They use the same samarium cobalt material and magnetic fields to set them in motion.
So it's literally like drilling its way through that liquid.
Drilling its way up.
Wow.
This is the biggest one. The smallest one is only 30 microns long. That's 30 millionths of a meter, about a third the width of a human hair.
So now, just in the last few years, we've actually been able to build small things of a similar size and shape to real bacteria that swim just like they do, potentially deep inside a person's body.
The magnet-driven robots in Brad's lab, the iBot, the FlagellaBot, and even a soccer-playing robot that his students created, are each no bigger than a dust speck. Brad's learned to modify his robots to overcome the physical obstacles in the microscopic realm. But he's only scratched the surface of the strange properties in that infinitesimal world.
An atom is actually a fraction of a nanometer.
Chad Merkin is an explorer and pioneer in this weird realm, the nano world.
You keep saying you're building things on the nanometer scale. I don't even know what a nanometer is. So this is a meter, this is a centimeter, this is a millimeter. Is this a nanometer? What's a nanometer?
I'm going to try to illustrate it for you. If we shrink you by a factor of 2, you're about the size of a small child. If we continue to shrink you by a factor of 2, 4 more times, you're about the size of a golf ball. If we go to 10, you're now the size of an ant. We keep going another 7 times, and now you're about the diameter of a human hair. That's roughly what we can see with the naked eye.